Hi, my name is Tan Hon, and today I'll be presenting the reservoir rock properties assignment project, which is the relative permeability curve. This is me, Tan Hon, and this is Geoffrey. So he will be presenting what is relative permeability, and for Jack, he will present on how to get the relative permeability curve. And as for Evan, so he will be present on the evaluation of the results. And lastly, Sujan, he will be presenting the conclusion part. Hi, my name. So what is capillary pressure and how to measure capillary pressure? So capillary pressure is defined as the pressure difference between the non-wetting phase and the wetting phase across the interface of two immiscible fluids, as well as the part of scale measurement. So there are actually three types of method that we have proposed to measure the capillary pressure. So the first one is the porous plate technique, followed by mercury injection capillary pressure, and lastly the centrifuge method. So for porous plate technique is actually the use of the low permeability water wet porous plate. So we are ensuring the inlet pressure will be the oil pressure and the outlet pressure will be the water pressure. So we are applying the formula, which is the PC, the capillary pressure, equals to the non-wetting phase pressure minus the wetting phase pressure. So we are starting with the low capillary pressure and wait until the equilibrium is achieved. And lastly, we'll try to calculate the water saturation by using the volumetric balance. So porous plate technique is actually an accurate technique, and followed by the second one, which is the mercury injection capillary pressure MICP method. So the core sample is placed inside the chamber, and mercury is then injected through the pump. So mercury acts as the non-wetting phase, while the air will act as the wetting phase. The volume of the mercury will be converted to the saturation of the non-wetting phase. So we are actually using MICP method to characterize the rod samples through the throat radius distribution. However, MICP method comes with a few of disadvantages. First of all, it would damage the core sample as we are using mercury. And next, MICP method sometimes is slightly inaccurate as we need to do the conversion for the lab measurement capillary pressure into the reservoir capillary measure pressure. So lastly, the centrifuge method. So we are actually dividing centrifuge method into the drainage and also the imbibition method. So drainage method, core sample will be saturated with water and then placed into the cell saturated by the oil, which is the non-wetting phase. So centrifuge will then centrifuge the core sample at several speeds from low to high, and lastly converted the speed into the rotational speed into the pressure. So by using the imbibition centrifuge method, so we're actually reversing the cell. We're actually reversing the cell, and then we'll use oil as oil is less than water. Yeah, that's all from me. Thank you.
So I'm going to discuss about the relative permeability, K relative. Before that, what is absolute permeability, K absolute, and effective permeability, K effective? K absolute is the measure of capacity of the road to transmit a single fluid, while the K effective is the permeability to each phase in the road where more than one fluid present. So the relative permeability is the ratio of K effective to a reference permeability K reference, which usually the K absolute of air or liquid. From this definition, we can know that the relative permeability will range from 0 to 1 as its numerator, which is K effective, won't be greater than its denominator, which is K reference. So
So next, I'll proceed with how to get relative permeability curve from the capillary pressure result. There are a total of three methods used to obtain the relative permeability curve. So for the first one, it is called parcel approach. In this method, we will use the capillary pressure data given to determine the relative permeability for the wetting phase, known as KRW, and the relative permeability for the non-wetting phase, known as KRNW, by using two equations shown here. Then, we can obtain several data points for KRW and KRNW. By plotting KRW and KRNW against water saturation SW, we can obtain the relative permeability curve for the parcel approach. Next, I'll continue with the second method used, and it is called Burdin approach. Similar to that of parcel approach, Burdin approach only has slight difference because the concept of tortuosity ratio is introduced into the equation. In this method, we will first determine the tortuosity ratio of the wetting phase and the tortuosity ratio of the non-wetting phase. And by considering them into the integral calculation, we can obtain several data points for KRW and KRNW. By using the same step applies above, we can plot KRW and KRNW against water saturation SW to obtain the relative permeability curve for the Burdine approach. Lastly, the third method is Brooke-Corey's relative permeability model. In this model, a capillary pressure function is introduced as shown by the first equation under this section. This equation is then changed into the logarithmic scale by plotting the graph ln PC against ln SW star. Then, the line of this graph can be represented by the equation highlighted in black color, and by considering the gradient of the line with negative 1 over lambda, the value of lambda can be determined. Subsequently, we substitute the value of lambda into the equation of KRW and KRNW to calculate the relative permeability for the wetting phase and for the non-wetting phase. And same method applies. We can obtain the relative permeability curve by plotting KRW and KRNW against SW. That's all. Thank you.
Now I will discuss the relative permeability curves we obtain from using three methods. Firstly, this is the relative permeability curve obtained by using Purcell's model. The orange line represents the relative permeability of the wetting phase, and the blue line represents the relative permeability of the non-wetting phase. From the graph, we can see that KRW starts at a low value at irreducible water saturation and increases exponentially when water saturation is more than 0.5 until irreducible saturation of non-wetting phase is reached. The KRNW curve starts at a high value and decreases sharply over a large range. This is due to the nature of the equation that includes a large area of error, hence it is inaccurate. Next, we can see that the KRW and KRNW curves intersect at water saturation equals to 0.69, which indicates both liquid flow at equal ease. From this graph, we can draw the conclusion that KRW curve plotted is close to experimental data and KRNW curve values are far from the experimental data. Moving on, the second model we employed is Burdine model, which is a modified version of Purcell's model by adding a tortuosity factor into the equation. From the graph, we can see that KRW starts at a lower value when water saturation is less than 0.7 and increases sharply when water saturation is more than 0.7. Meanwhile, KRNW curve starts at a high value at irreducible water saturation and decreases in a smooth downward curve as KRW increases. The crossover of KRW and KRNW occurs at water saturation equals to 0.69, which indicates both liquid flow at equal ease. From the shape of the graph, we can conclude that KRW curve plotted fits the experimental data better than the KRNW curve, and it is more accurate for the imbibition relative permeability curve. Lastly, the last model we use is Brooks-Corey model, which is an improved version of Corey's model where capillary pressure function is modified to a more general form. From the graph, KRW starts at a lower value when water saturation is less than 0.5 and increases sharply when water saturation is more than 0.5. KRNW starts at a high value of 0.5 at irreducible water saturation and decreases as KRW increases. The same crossover is observed at water saturation equals to 0.69, which indicates both liquid flow at equal ease. Out of the three models, this is the best model to represent the experimental data as it is the most accurate because KRW and KRNW is less or equal than 1.
In conclusion, we have utilized three methods to determine relative permeability. It is Purcell method, Burdine approach, and Brooke-Corey relative permeability model. By employing this method, we have successfully generated three graphs to assess relative permeability. Among these methods, we have identified the Brooke-Corey relative permeability model as the most accurate for determining permeability, as indicated by the KRW and KRNW values on the graph being less than 1.